Good afternoon everyone, this is Arun Sharma from midas, and today we'll be covering suspension bridges. These are the contents of our webinar today. We'll be first talking about different analysis procedures that are required for a suspension bridge analysis. So first we'll be talking about completed state analysis, which is also called linearized finite displacement method. Then we'll be talking about construction stage analysis, which will be backward and will include geometric nonlinearity. Then we'll be going through the overview of the bridge, the suspension bridge that we'll be modeling today. And then we'll be talking about the various modeling features we have for suspension bridge and how we can obtain initial cable forces using them. So as I mentioned, we'll be talking about the analysis approaches. So the first one is completed state analysis, and as you can read from the literature, this is an excerpt from our tutorial that is available on our website, which you can download for free. And it says that completed state analysis is at this stage the structure is in balanced condition under self-weight, and the deflection due to self-weight has already occurred. This stage is referred to as initial equilibrium state of suspension bridge. The initial equilibrium state analysis provides the coordinates and tension forces in the cables. This state is analyzed to check the behavior of the structure under additional loads such as live load, seismic, and other wind loadings. So basically, when the structure is completed, you can call it as the final construction stage. The structure and before applying additional loads, that particular phase of structure is called initial equilibrium state, or the completed state of the structure, where just the self-weight is acting on the structure. So when we do this type of analysis, we are able to obtain initial cable forces and the coordinates for the cables. Then we can go on refining it as and when required. On the other hand, we have construction stage analysis, which is used to perform and see the behavior of structure during the construction stages. So we can check whether the structure is stable throughout each and every construction stage. You can choose to do different type of eigenvalue analysis and see whether what will be the behavior of the structure during construction stage as well as after construction stage. And the construction stage analysis for suspension bridges, as you can read from this excerpt here, is the construction stage analysis is performed in backward sequence from the state of equilibrium as defined by the initial equilibrium state analysis. So basically, first we have the completed state ready with us. We do the analysis, we obtain the coordinates and the tension forces for cables, and then that is from there we move in the backward direction to the very first stage. Basically it's a deconstruction, you can say. So it's a backward construction stage analysis, that is, the starting point is from the completed stage to the backward. So the few keywords that I pointed out on the very first slide were linearized finite displacement method, large displacement or geometric nonlinearity, and backward. So I'll be covering what all we mean by stating them. So completed state analysis, since as sufficient tension forces are induced into the main cable and hanger under the initial equilibrium state loading, it is possible to perform a linearized analysis for the additional static loads by converting the tension forces in the main cable and hangers into increased geometric stiffness of these components. This linearized analytical procedure to convert section forces to geometric stiffness is referred to as linearized finite displacement method. Long story short, you obtain the initial cable forces in cables and hangers due to the initial or the completed state loading, and then you converted that initial cable forces into increased geometric stiffness of that section, and then you just apply additional loads and do the analysis. So this type of procedure is called linearized finite displacement method. Alright. Whereas on the other hand, construction stage analysis suspension bridges exhibit significant nonlinear behavior during the construction stages. The effect of large displacement cannot be ignored here. Hence, in carrying out the construction stage analysis, large displacement theory or the geometric nonlinear theory is applied, in which equilibrium equations are formulated to represent the deformed shape. So what we do in construction stage analysis is that we don't directly convert or the geometric increase the geometric stiffnesses just from the cable forces. We take into account when a structure is removed in backward construction stage analysis, how is the force distribution. So at each and every construction stage or deconstruction stage in this type of analysis is considered as independent from each other, and for each stage there exists a set of equilibrium that needs to be maintained for that stage to be stable. So this is what we mean when we say that the large displacement theory is applied, in which equilibrium equations are formulated to represent the deformed shape. So whatever is the deformed shape that is coming, it is stable or not, it's based on the equilibrium equations that are formulated based on the removing or the redistribution of the forces when a particular segment is removed from the structure in backward construction stage analysis. So I'll be covering these two types of analysis while going through the session today. So now moving on to the overview of the bridge. This is what we'll be modeling, and this is how we'll be doing it. So first we'll start by modeling the bridge geometry, for which we'll use suspension bridge wizard, and through this we'll define geometry, sections and the deck weight of the structure. Then we'll run suspension wizard to generate or to obtain cable forces or the cable coordinates and initial cable forces. So basically at this point of time we just have the dead weight of the deck acting onto the structure, for using which the coordinates for the cable, that is the catenary cable equation is used and the coordinates for the cables are generated for the geometry. Along with this we also get set of initial forces which are used for small and large displacement analysis, which I'll cover later on. Then after this we'll modify the model, that is we'll modify the boundary conditions, since the deck are initially not rigidly connected but they are pin connected throughout the length, and then later on they are rigidly connected. We'll model those pin connections. We'll also modify the geometry by adding transverse pylon connections, and then we'll add some additional loads onto the structure. So basically we are refining the model that we obtained from suspension bridge wizard, and then we'll run suspension bridge analysis control for accurate cable forces. So based on these more realistic or site dependent conditions we apply here, and then we run a suspension bridge analysis control for accurate or further refining the cable forces that we have obtained. Through this run we get initial forces for large displacement, initial forces for small displacement. I'll cover what is large displacement, small displacement when the time is right. I mean when I move along the webinar. Then since we are first looking at completed state analysis and we don't require any nonlinear behavior, so we'll remove the nonlinear and the suspension bridge analysis control data for this linearized analysis, and then we'll modify the model for additional loading and boundary conditions as per completed state model, and then run the analysis. So in the analysis we'll be doing just a linear analysis for small displacement, and then I'll be talking about some results on this model. Then we'll move on to define the construction stage analysis model. where we'll be defining or modifying the geometry of the bridge by adding construction stages to it, for which we'll be defining the structure, boundary and load groups, and then generating the construction stages. Since we have already obtained the initial forces for large displacement, which will be used for construction stage analysis, we'll need not go and modify anything else in loading. We'll just go ahead and run the construction stage analysis for backward construction stage analysis, and then we'll be talking about some more results. Now this is how our suspension bridge will look like. The geometry is shown here. It's a 3-span bridge where the main span is 400-meter long. Then the two additional spans are 125. The side spans are 125-meter each. So the key component in suspension bridge analysis is determination of initial cable forces. And in midas civil we have two components, as I mentioned. One is suspension bridge, one is suspension bridge wizard, and another is suspension bridge analysis control. So suspension bridge wizard can calculate the initial cable forces for self-weight or the weight that you have defined in the wizard, whereas suspension bridge analysis control is something which follows the wizard, or you can start from scratch by yourself, which will allow you to calculate the initial cable forces for self-weight and any other additional superimposed dead loads. So I'll be covering about the initial forces for geometric stiffness right now. So when we'll run the analysis or run the suspension bridge wizard, we'll get initial forces for large displacement, initial forces for small displacement. These are just based on the given loading and the given geometry and given boundary conditions. The program generates these two initial forces. Now these initial forces are used to represent the initial equilibrium state in construction stages when we talk about large displacement, and then these forces are used to modify the geometric stiffness of the section and then use it during the construction stage analysis. Whereas the small displacement analysis is the member forces that are in the structure due to the external loads for linear analysis. So initial element forces are used to calculate geometric stiffness in general linear analysis. So in a nutshell, or long story short, or in the layman terms, the initial forces for large displacement are used for construction stage analysis for large displacement analysis, which means it is meant for non-linear analysis, whereas initial forces for small displacement is meant for linearized finite displacement method, and it is used for just linear analysis, that is for completed state analysis, and that's the end of the story. So it's very simple in the suspension bridge wizard or suspension bridge analysis control in midas civil to understand these concepts and see them in action. So from this point onwards, I'll go into the model itself and start the modeling. So now I'll start by defining the the geometry based using suspension bridge wizard. So I'll go to model, go to structure wizard, and then I'll go down and select suspension bridge. And let me first change the unit systems to ton F, ton force, and meters. I'm sticking to these units because these are the same units in our tutorials, so that when you go back and you want to go through the complete video of this webinar or go through the tutorial yourself, you'll not be able to you will be able to relate to what all we did today. So go to model, structure wizard, and then suspension bridge, and then we'll enter the coordinates here for the overall geometry, and all these coordinates you can find out as given in the bitmap image right here. So you can see what is A, what is A1, what is B, C, D, E, and all these uh, variables. A1 being 3.6, 0, 20.72, B being 128.6, 0, and 60.8, and C being that is the sack point, which is user defined, is 328.6, 0, and 27. Since it's a symmetric bridge, I'll not be defining D, E, and E1, which is on the other side, and then I'll enter the height as 60.8, and then I'll go to material. I'll directly import the material for the time being to save some time here. So these are the material that we'll be using for cables. The moment I click OK, you can see the material properties imported, and as well as you can see it under Works tab. We'll go to section, click import. From the same suspension bridge model, I'll import the section properties also, and you can see all the section properties in this bitmap image right here. And if you want to see the material properties, you can just double click and see them. They are all user defined material properties where we have defined the modulus of velocity, a Poisson ratio, and the weight density. So in midas you can handle concrete, steel reinforced concrete, and any user defined material property, even wood. Once we have defined them, then we can assign the or we can match the material properties with the elements here. So we'll have for main cable type of material, side cable we'll have cable, typical hanger, end hanger will all have hanger material properties, and deck will have deck, and pylon will have pylon material properties. Same thing will go with section, cable, hanger, deck, and pylon. The width of the deck we are defining as 11, and for the unit weight what I'm doing is clicking on advanced and defining as point loads on the left side. Since it is symmetric, it will be uh, uh, copied on the other side. And this is on the center span, which will be 31 times 52.9375, and then click OK. So we have not defined the self weight or the unit weight directly. We have just defined point loads at all the anchor locations here. And now we'll define the shape of the deck. You can consider the slope. If it's asymmetric, then you can have left and right slope. Right now I'll just have same slope on both sides, and the arc length will be 650. Once we have entered this, then we can enter the hanger distance on the left and the center. So it will be 10 at 12.5 meters, and the other one will be 32 at 12.5 meters. You can click on drawing and see the preview of how the model will look like. And if you want to reuse these values or similar wizards, similar settings, you can always save them as some name, and then later on you can just click on them and click open to bring back these settings. Then you can click OK here, and the program will ask you, the moment you click OK, the program is about to execute the suspension bridge wizard, and therefore it asks you to first save this file with some name. So I'll just say suspension bridge SP, and then click save here, and now the program will run the analysis and generate the geometry. So if you noticed, we just defined the top of the pylon, the points A and A1 here, the height of the pylon, and the sag point. We did not define the coordinates for this cable or the side cables. So based on the loads that we define in the height, the program automatically computed these with the initial forces. So as you can see here, the initial forces are generated based on this, uh, based on the wizard settings as we have entered. Now you can go ahead and modify them as I mentioned previously. So what I'll do is switch to a wireframe right now, and first, because it's a curved deck, so I'll move the pylon nodes to merge at that location. I'll just single select them, right click, go to nodes, and then translate. I don't know what is the height here, so I'll click on move, and in this green field I'll just click on the node from where I want to go to other location. Let me click on the node right above it, and I just want to raise it in the Z plane. So I'll enter 0, 0, the height here, and then check on intersect frame elements and click apply, and then the node will move up. And now I want to divide my pylon into number of pieces so that I can connect them in the transverse direction. I'll right click, go to elements, divide, and then I'll divide into unequal distances starting from top as 1.75, sorry, 1.25 comma 18.75. Click apply. Having done this, I can switch to ISO view here, zoom in so you can see the element divided. Now I will right click, go to elements and create element, where I'll select the material as pylon and the section is pylon trans, which means transverse, and I'll just click on the node and then go all the way across it like this to create 3 connections there. Similarly, I'll do it here on the other pylon, and I don't want the topmost connection to be there, so I'll just click on them and hit delete from the keyboard. So basically I'm quickly modifying the geometry as per my requirements. Now I'll go ahead and modify the boundary conditions. For this just for your information, you can see that there are 49 rigid links. So if I zoom in at this location, you can see the hangers are there, and then the girder is in the center, and they are connected through rigid links, where the girder node is master and the other 2 nodes at the 2 ends of the anchors for the hangers are the slaves to that node. Now I'll undisplay them again, and now I'll apply support and you can also see the program has already generated some supports, so you can right click and display them on the screen. So the cable anchors are there. It's an earth anchored suspension bridge. There is anchorage at there are supports at the base of the pylon, but the decks are at the two ends need to be supported. So I'll just select the 2 extremes here, then right click, go to boundaries, support, and then I'll fix all the degrees of freedom. That means dx, dy, dz with 3 displacement degrees of freedom and 2 rotational degrees of freedom, that is ry and rz. So it is basically allowing the rotation about the y axis. So ry is allowed at these nodes, and then I'll click apply. Now I'll go ahead and as I mentioned before, the before the deck is rigidly connected uh, to the hangers or to the structure, they are kind of suspended from the top. So basically the excuse me, let me bring an image onto the screen so that will help you understand this better. So basically we are trying to simulate this behavior. The deck is suspended by the hangers only, the sag point is there, so we want to simulate this behavior. So as you can see, there will be no transfer of moment between the deck locations, I mean the deck connections. So we'll go for a, pin connection at all the nodes on the along this girder, and we are doing this to get refined geometry and initial forces in cables using the suspension bridge analysis control, which I'll be using very shortly from now. So for this I'll just enter the element number that I want to use. So to start with, I'll start with the girder that is connected to the pylon. I'll right click, go to boundaries, and in the boundaries I'll select beam and release, and here I'll select I want to release the moment on both ends for now. So my and my at I and j are released, and I also want to since it's a kind of roller support um, at the pylon connection, so I'll also release the fx at the jth node for these two elements, and then click apply, and then I'll repeat the same thing for the deck connected to the other side of the pylon. So I'll select them, and fx at ith end of this element will be released. So I'll just click apply here. That's it. And now I'll select all the girders and go and modify their um, apply a pin release uh, on their I and J end as and when required. So I'll directly go to select element by identifying or by numbers. So I'll enter the element numbers, which is 204 to 211 and 230 to 243. Hit enter, so you can directly see all the members that I want to select have been selected here. I'll define a boundary group which I'll use later on by the name pin connection. Click add here, click close, and then select and assign all these pin connections under this heading. So I'll remove I'll just apply the bending moment by release at the ith end of these members. Click apply, and then I'll select the other side. It will be 214 to 228 and 246 to 253, and then hit enter. You can see the other side of the girders, or the other side of the span is selected. This for this span will release the bending moment at the jth node of the elements, and click apply. I'll not dwell deep into the beam and releases here and Y, I, and J. All these are quite small but important details and are given in the tutorial. So I'll encourage you to definitely go through the tutorials, because if I cover everything here, the session will be never concluded. So having defined these releases, we'll now go ahead and create two structure groups. So I'll go to group tab, right click, go to new with three dots, enter the name as nodes to be updated, click add, and the other group will be sag points, and then click add. And now all the nodes that need to be updated after upon running of suspension bridge analysis control under the revised boundary conditions, we need to assign them right here. So I'll go to nodes by entering, select nodes by numbers. So I'll enter the node data right here, 44 to 52, 104 to 112, 114 to 144, and 146 to 154. When I hit enter, you can see all the nodes except the pylon ones are selected along the cable. Then I'll just click on the nodes to be updated group, drag it over the screen, and drop it. In this manner, you can see 98 nodes are selected. Now I'll go ahead and define the nodes to this group, which is sag points, which is basically the two nodes on the main cable at the sag point, which will be 27 and 129, and you can see the nodes right there. I'll drag and drop it over the screen, the sag points. Now we'll go to loads, static load cases, and we have as you can see, the program has already defined a self weight for us. So we'll go to loads and select self weight, and let me put this self weight into a structure group, a load group, which I'll use later on. So let the name be self weight, click add and close. Basically this self weight load group is required for suspension bridge analysis control also. So I'll select the load group here and modify my existing self weight, which is right now under default group. So I'll click on self weight and then click modify. So you can see the group is modified right here. And now I'll add some additional load onto the nodes. So I'll right click, go to load, and under load I'll select nodal loads, the load case and the load group remaining self weight. I'll add minus 26.469. If you remember, this is half of the value that we entered in the suspension bridge wizard. So I'll go to wizard here, and if I go to advanced, you can see 52.97935 and half is 26 point something, which we are entering now. Basically this load was applied directly to the deck to get the geometry, but now we are applying the load to the appropriate anchor location. So we are dividing it into half because there are two anchors per hanger, so one here, one on the other side. So therefore now I'll select the nodes on which I want to apply this loading, and that will be 54 to 102 and 156 to 204. So you can see all the anchor points are selected. In fact, you can go in, zoom in and select all of them, or there are several other ways of selecting this. I'm just using this number approach so that I need not move my model several times as we are going through some network issues or the lag between the transmission and reception. Then you can click apply here, and you can see the loading being applied. Now we can close this, go to analysis and select suspension bridge analysis control data. But before that, let me switch to the works tab so that you can notice the difference here. So going to analysis, suspension bridge analysis control data, number of iterations is 10, nodes to be updated. I'll selected the structure group as nodes to be updated. Then sag point group, I'll select sag point, and here there are some other refinements that that are possible for suspension bridge analysis control to take into account. It can be a constant horizontal force of cable, which you can use to apply onto the pylon if needed. Then furthermore refinement can be done for hanger bottom point Z displacement conditions. So you can select the um, I mean, these are basically different constraints and settings that are field specific or your model specific, and you can go ahead and modify them. And more detailed literature is available in the tutorial and on our website, so feel free to browse those pages there. Now here I'll stick to some simple straightforward approach for the time being. So load case being self-weight, factor being 1, and I'll click add. So based for this load case that includes the self-weight as well as the point load that we just applied, the program will modify or do the iterations and update the nodes that need to be updated, keeping the sack points as same because these are fixed. They are user defined, they will not be modified, and everything else will revolve around them. And in order to do this, the program will calculate what is the additional forces required in the cable or relaxation required in the cable. So basically what all uh, initial forces for geometric stiffness you have obtained here will be revised and will be filtered or made more accurate. Same thing for initial element forces for small displacement. I'll click OK, and you can see here the iterations are done. And now we can now move on with the modeling and oh, my bad, sorry, we need to perform the analysis. That's why I was thinking it's just 0.41 seconds from the previous one. So therefore I'll click on perform analysis, and now the program will update and do the iterations. So it took 2.25 seconds, and now you can see that initial forces for geometric stiffness are updated, and the program has calculated equilibrium element nodal force for the corresponding structure. Now these equilibrium element nodal forces are used when we do the backward construction stage analysis. When a certain set of elements are removed, how the load is to be redistributed so that there are no significant deformations or instability in the structure. So, and the initial forces for geometric stiffness, as we all know, this will be used to modify the geometric stiffness of the sections in order to carry out the geometric nonlinearity. And the small displacement, initial forces for small displacement are meant for completed state analysis, which is nonlinear, or sorry, which is a linear analysis. Now once this analysis is completed, now we can move on to modify the geometry for linearized analysis, and we don't need the nonlinear analysis, so we'll just remove nonlinear analysis. We don't need suspension bridge analysis, so we'll remove suspension bridge analysis, I mean the controlling data. And now with no such control, it is just a linear analysis model. So for linear analysis model, it will not use or ignore all the large displacement values that are there, and while and just the initial forces for small displacement will be used. If you want to see their values, you can right click, go to table, and the program will show you all the values that are calculated based on the geometry and the loading that are specified for trusses and beam elements. So now the final touches is I want to get as let me bring back that image. Now since this kind of setting or the boundary condition was needed to assess the geometry and the initial forces for updating the cable forces, but in real completed state analysis, this complete deck is rigidly connected to the structure. So what we'll do is we'll delete all the pin connections that we just created, and we'll do that in this manner. So we know the first type 1 is 00010, and so that means at ith end, at ith node my is released, so I don't want this set of links, so I'll delete them. And not the link, sorry, the beam and releases, and then I'll delete the other one also, and I'll modify the type 1 and type 2 now. So I'll go right click, go to properties, I'll check off the release at ith end, click apply, and the moment I do that, if I go to the elevation and if you try to look closely, these two are modified here. Now you can see just one circle, otherwise there were two circles at I and J end. I close this, and then I'll go to the other one, right click, go to property, and just check off at J at the end, and then click apply. So now you can see now since we have a roller condition at the connections, or the bearing is there, which will allow the movement of deck over the pylon transverse connection. So we have applied this kind of beam and release. And now since the main cable is connected to the deck rigidly, we will apply a stay link element. So what we'll do is go to boundaries and select an elastic link, and here we'll enter the stiffness along the x-axis, this is which is the global x-axis but local z direction, as 1 10 to the power 11, and I'll just rotate it to a side, and I'll create the link once and it will be copied to the other location. So the width of the deck is 11, so I'll select y-axis and 11 meters, and the nodes, I'll just go to the appropriate node, which happens to be node number 27 and 78. So this is the sag point here, so I'll click on 27 and then click on 28, and you can see if I zoom in at this location, you can see the x-axis is vertical, y is perpendicular, and z axis is along the global x-axis. So the stiffness along global x-axis for this link element has been increased significantly, so that this link will compensate for the movement of the deck and they keep the cables intact with the deck at this location. So having done this, now we can apply some additional loads onto the structure. Let's say, this model as such is our final completed state model. Now if you want to see the effect of some vehicles on the structure, we can do the live load analysis, you can just apply some other kind of wind load analysis, seismic analysis, whatever you want to do. Your suspension bridge is now ready to take care of all the static loads for final state analysis, because we have already applied sufficient cable forces to take care of all the other static load analysis. Just to give some brief example, let me enter some load cases here. User defined type, load case 1, click add, 2, add, 3, and add. So I've defined 3 load cases. Basically what I'll do is apply point loads at different locations, which will represent either the vehicle or pedestrian load, but the magnitude is high enough, it's 46 ton force, so this is equivalent to comparable to a vehicle. Excuse me. So what I'll do is right click, go to loads, nodal loads, and here select load case 1, LC1, FC will be minus 46. The loading will be applied at the right at the deck or the girder under the sag point. Then I'll change the load case to LC2, value remaining same, and that should be applied at some distance, let's say 223 right here. Then I'll change it to LC3 and the value remains same, and let us apply on somewhere here. So that will be node number 210, and then click apply. So we have applied 3-point loads at different locations, and now we are all set to run the analysis on this model. And you can see in the message window the analysis being performed. It just took about 1 second to complete this simple analysis. And now I'll quickly show you some deformation results. So right click, go to deformation, deform shape. Under self weight you can click undeformed legend, click apply. So this is the, I don't know if you can see on your screens clearly, there is a faint line at the backdrop which shows the undeformed shape, and this is showing the deformed shape. But if you see the magnitude, it's quite less, so this is a exaggerated image. So you can control the scale factor, let's say 0.2 times, click apply. So now you can see more realistic deformation, and then you can see due to say load case 1 how much is the deformation, load case 2 how much is the deformation, and so on and so forth. And then this is load case 3, and the load is right here. I can choose to display the nodal loads. So whenever I'm seeing this is load case 3, this is load case 1, this is load case 2, and all these values can be extracted in tabular format in no time right here. And let's also review the cable forces, which will fall under the category of truss forces. Let's say load case 1, click apply. So you can see the cable forces right here, and if you want to see them in tabular format you can select that load case and just select the cables, and you can see the values. Now point to be noted here is the cables already have initial forces in them, which is due to the self weight of the structure, or the self weight group that we the load case that we added. So all the values that you are seeing here are over and above that initial value. So this is the additional forces that are there. So if you want to see the summation of the two, or take into account this cable force also while computing or modifying the geometric stiffness, what you can do is you can just go to load, go to initial forces for small displacement, and then there exists initial force control data. You click on this, you can just simply say add initial force to the element force, and then select load case 1 and then just click OK, and then you can go ahead and perform the analysis again, and then you will get the modified values. So this completes our completed state analysis, and now I'll move on to the construction stage analysis model. If you have any questions till this point, you may ask really quick, otherwise I'll move on with the second part of this session, which will approximately take 25 to 30 minutes from now. Alright, so hold on to your questions. I'll proceed from this point and directly move on to define construction stages. So let me save this file with the name as, let's say, construction stage CS. So we have all the loadings right here. Let me undisplay the loadings. We have all the initial forces already set up. So this time it was just the initial forces for small displacement that were reused. Next time in construction stages, the large displacement values will be used. So for this, all we need to do is just go to, let's first start by defining structure groups. So we'll go to groups, right click, or I think I should take this towards the end because it will take time. So let's do other stuff first. Let us generate construction stages. So I'll click on that icon to that says define construction stages, then click generate. Enter the name as CS for construction stages. Suffix can be 0, comma 2 to, or say 0 to 7. I want to have 7 or 8 construction stages. So 0 to 7 construction stages. Then click on save result for stages and then click OK. So you'll see 8 construction stages generated, and then we'll go on manipulating them from little while from now, and then click close. Other things we need to do before this is go to loads, go to static load cases, delete the user defined load cases that we were dealing with, modify the self weight with CS, that is the construction stage loads, because you want to see its effect during the construction stage. Click modify, and now we'll define the groups. So right click, go to group with new with 3 dots, and enter the name as S underscore G, that is structure group, and suffix will be 0, 2 to 7. I'm doing this on purpose. I want one. I don't want to have a structure group 1 because these suffix. Now here's a tip for you. These suffix are same as construction stages, so it will be easier for me to remember that which group needs to be activated in which construction stage. So I don't want to activate or deactivate anything in CS1. Therefore, I didn't create a structure group by that suffix. I'll click close here. And for the very first stage, since it's a deconstructing construction or backward construction stage, so what I'll do, let me bring back the model file. And so this is what the construction stage, or this is how the construction stage will look like. It'll have the completed model. Then we'll start by applying pin connections for the deck again, because this is what the final model looks like. Or either way, I should let me explain you in this direction. So first we'll have the pylons and the cables with the sag there. Then we'll start construction from the sag points and then move towards the 2 ends of the pylon. Then the entire span is created, and then we'll move from the 2 extreme ends and start adding deck under these side cables. And once the side cables are connected, I mean the deck is completed, it is still flexible and not rigidly connected to the with the adjacent members. So once the entire bridge is stabilized, then we'll completed, we'll make them rigid. So that's the real role of pin connection right here. And we'll also add the stay member in the final or the completed state, which will not be there in the following construction sequences. So this will this is how our construction schedule looks like. First stage, we'll activate the complete structure, we'll activate all the boundaries and the stay conditions, and we'll activate the self-weight load group that we have defined. Then next construction stage, we'll not activate or deactivate any structure group. We'll just take out the we'll just activate the pin connections, that is to make the deck not connected rigidly or we're having pin connections, and we'll deactivate the stay boundary conditions. And then we'll go on deactivating. As you can see here, it's under deactivate tab, deactivating SG2, SG3, SG4, SG5, SG6 and 7, and so on and so forth. So let me show you how we can define the structure groups to start with. So let me zoom in at this point. I'll just use single select and select the members that form my structure group 2. Or first of all, let me define the complete structure group. So let me select all, and then click on SG0, drag it over the screen and drop it. So this is our final state model, which is under SG0. And now I'll select the members that are following in other structure groups. Then click on SG2, drag it to the screen and drop it. And then in order to make the selection more visible, I can right click and click inactive. So now you cannot see them on the screen. Then you can go ahead and select 1 2 3 4 5 hangers here, and similarly 1 2 3 4 5 hangers here, and then put them under third SG3 group, and then right click and select inactive. So in this manner you can go on defining the members. So what I'll do is open a file where I've completed this repetitive steps, and that will be this model. So if I come to the structure group, oops, not this one, CS1, I guess, yeah. Anyways, let me quickly modify this. Excuse me. So here you can see, if I just double click on the structure groups, they are put under different structure groups. The members are assigned, and then we have made a structure group for pin connection members so that we can identify which members are to be supposed to have pin connections. And we have already defined the pin connections from the we did in the previous previous model file for completed state analysis. Let me just right click and display. So you can see green circles that go to show that the pin connections have been defined, and they have been put under this pin connection boundary group. How to define boundary group is very simple. You just right click, go to new with 3 dots, enter the name, and then click add. We have also defined 2 boundary groups, which is BG and stay. And now what we'll do is define all the other boundary conditions to this boundary group BG. So what I'll do is select everything, select all, and then click on BG and drag it over the screen and drop it. And now I can specify what all things I want it to have this boundary group. So I'll just directly click OK. I'll select all the boundaries that are there and put them under BG group. And now I'll select everything and then drop the stay boundary group. And then I'll specify I just want to select the elastic link that I've defined under this boundary group. So I'll leave elastic link checked on and then click OK. So now if I double click, you can see that these nodes are selected, which will have the stay element defined. If I double click, you'll see the boundary group will have all the other boundary conditions defined. But if you recall, it is supposed to have all the boundary conditions except pin connections. So what I'll do is unselect everything, just select the pin connection structure group, and then click on pin connection and drop it to the screen, and check off everything else but beam and releases, and then click apply or OK. So now if I double click, you can see that these boundary conditions have been assigned. These are the boundary conditions in BG group, and then this is the boundary condition in the stay group. So this is how you can define boundary groups in no time. Having done this, we'll go ahead and define the construction schedule. So what I'll do is, let me just delete this and recreate it, because I realize this model file already has the construction stages defined. So I'll delete them, then I'll click generate CS027, check on save result, and then click OK here. And now I'll go on modify each and every construction stage. So this is the first construction stage where the complete model is activated. So I'll just click on SG0 group. This is the activation box, this is the deactivation box. I'll keep it under activation box. Then I'll move on to boundary tab and click on BG, that is the boundary conditions, all the other boundary conditions and stay boundary condition, and click under activation on add. Then I'll move on to the load tab and click on self-weight and click add. Then I'll click apply. So that in this manner I have defined construction stage 0. I'll move on to construction stage 1. Now until and unless you deactivate anything, everything is carried forward from previous construction stage to the following construction stage. So this means if you don't see self-weight under activation tab, this means but you activate it in the previous construction stage, it will automatically be carried forward to the subsequent construction stage. Same goes with boundary and same with the elements. Now I'll click on in this construction stage, you'll see pin connection being activated, stay being deactivated. So I'll go to boundaries, click on pin, click add, it's being activated, and stay will be deactivated. So I'll go under deactivation tab and click add and then apply. Having done this, I'll change the construction stage to CS2 and go to element tab, click on SG2, click add. Sorry, my mistake. SG2 is the structure group that is being taken out, so it will go under deactivation tab. Then click apply. And also, while deactivating any member, midas gives you the flexibility to consider the element force redistribution. If you don't want to redistribute the entire force that was supported by this member, you can choose any number less than 100 for that. 100 means the complete force is redistributed to the neighboring or the adjacent members. Then you click apply. Then you can change to CS3, structure group 3, under deactivation tab, add, apply. Fourth stage, SG4, deactivate, apply. Fifth SG5, sixth construction stage, sixth SG group, under deactivation, apply, and seventh, under seventh, and then click apply. And then you can close this and close this as well. Now once we have done this, you can cycle through the construction stages and see for yourself how the construction stages are laid down. So I'll go to the and before this, let me also go to display and select all the nodal loads to be displayed. Go to boundary tab and all the boundaries to be displayed, which includes all the elastic link and the beam and releases and the support, and then click OK. So you can see all the things are displayed on the screen. Now I'll change the construction stage to CS0, which is the final state, and you'll see that only the deck to pylon connection is roller there, which will allow the movement, as well as the the beam and releases are there to simulate that, and we have the stay member there. So let me zoom in at this location. You can see the yellow color thing is the stay member right there. So this is the final state model or the completed state model. Then we come to the first construction stage, and then you see the all the deck individual members are pin connection. Then second stage, CS2 will be this member is taken out. Third will be in the backward order, and this will be the seventh construction stage. So this is how we define the construction stages. Now we can go ahead and define the construction stage analysis control. So you go to analysis, construction stage analysis control, and here you make sure we checked on include nonlinear analysis. Under nonlinear analysis, you can specify displacement norm and other nonlinear analysis control criteria, and then you can choose whether you want to have each state um, analyzed as independent or accumulated. By independent, as the name says, each stage has no relation with the following construction stages. It will be analyzed independent from each other. If you choose accumulated, then the effects are accumulated together as we move on. Since it's a backward construction stage analysis, it is the independent stage that we follow. And make sure to check on include equilibrium element nodal forces, because when we'll be removing members, the program will apply equal and opposite external forces, uh, which will be developed internally by the program in the members, so that the structure is stable. And these forces have been automatically obtained by the program with the help or with the aid of suspension bridge analysis control data. And make sure you are in the base construction stage when you are changing, because I got an error message which is now removed here. So I'll go to analysis and construction stage analysis control data and then click OK. And if you come to works tab, you can see the analysis control data right there. And now we are good to perform the analysis. But while the analysis is being performed, let me open another model file which will have the completed state analysis. Oh, okay, I'll rerun the analysis for this file as well. And you can see under the message window the analysis being performed, and the analysis take about roughly 4 seconds for this backward construction stage nonlinear analysis. So you can appreciate the speed of the engine. I agree the analysis was relatively simpler as compared to the real structures, because there you can have time dependent effect if you want for different type of components of the structure. You can have other sets of loadings. It can be made more realistic, but certainly this is a definite time saver when it comes to generating the or obtaining the initial forces for large displacement, small displacement analysis. It definitely saves a good amount of time. Now we'll move to construction stage 7 here, and let me switch to the side or the elevation view. Right click, go to deformed shape, summation loading, and then click undeformed shape, legend, and click apply. And here you can see this is the normal shape, and the program and the cable have gone all the way up. But if you see the value, it is just it's fairly less. So what I can do is reduce the scale to make it more realistic. So this is the dark line shows the deformed shape of the cantilever, or sorry, the catenary, and the gray line which is in the backdrop shows the undeformed shape. Now if you want to see how the sag or the sag points are deformed during the construction stages, you can go to result, stage step history graph, and then you can select displacement and click add new function. Enter the name as sag, the node number being the obviously the sag point node, so that will be 27, and the component being DZ, and then click OK. Then all the other things are mode is multifunction, last step of every stage, and step stage graph you want to see. You can see this result against time as well, but here we'll have stage step. Check on the function name, enter the graph title as sag, and then click graph. And if you see, this graph is created. So this is the last construction stage. I mean, this is the first construction stage or the completed state, and the direction of backward construction stage is this way. So if you want to interpret from beginning of the construction stage, so this will be the deformation at the sag, and then when you start constructing, it will move in this direction, and then finally it will meet absolutely zero deformation. So this is what we planned for, and the program gives you the amount of deflection you can expect um, during this construction of this bridge. Then this was the sag graph that is generated by the program. Then similarly we can see in the same construction stage the deformation. For suspension bridges there is something called setback. If you are not familiar with this term, you can go through our tutorials for more information or search internet. Setback is a kind of horizontal camber that is provided for the pylons. Basically, if the pylon, I mean the construction is started with vertical, absolutely vertical pylon, and the length of the uh, main cable being the final length of the completed state. Then as and when you start construction, you will see that the pylon will bend inside, and there will be cable slip occurring over the pylon. So in order to avoid this kind of pylon slip, and in order to avoid any unbalanced uh, uh, bending moment coming into the pylon, what construction engineers do, or the construction practice says, is we apply some wires or and pull the pylon back while it is in the initial stages of construction. So basically we apply a force deformation in the other direction, so that once the entire bridge is completed, it comes back to the vertical position. So this horizontal camber is called setback, and you can assess how much setback is required uh, through this kind of analysis. You can go to undeformed shape and then click on legend and select the X component because it's horizontal. So here you can see that this is the deformation that is occurring in the X direction, and the pylons are deformed this much. So you need to apply a horizontal camber of equal to this value as given by the program by pulling them from using some additional ropes or cables from behind. And when the structure will start forming from the center towards the outer ends, the pylon will become vertical because the length of the cable is fixed and there is no slipping occurring on top. So you can generate, you can have a better visualization of this if you go to stage step history graph, and here you can click add a function, enter the name as right tower. Basically you can enter any name you want, and the node value, node number will be at the top of that tower, let's say 43, and the component will be dx. Click OK here, and others being as set as default. I'll click on tower, I'll enter the name as set back graph, click graph, and this is what the program generates. So at the beginning of construction stage, again it is the backward construction stage. Direction is from the left side towards the right side. So this is the final state and this will be the initial state. So this is this much from the zero level that the camber should be provided for the vertical pylon, and this is how the deformation will occur, and then it will converge, and by the end of the construction you will get perfectly aligned absolute zero value and straight pylon as desired. So the program is able to predict all these variations. That is very useful while you are going ahead with the construction of suspension bridge. Now let's see some more of the results. Let's go to a different construction stage, right click, let's see member forces. We go to beam forces and moments, click moment, and then click legend and click apply. Sorry, let's go to diagrams, my solid fill, apply. So you'll see that there is absolutely no bending moment coming into the deck as we desire, and there will be some unbalanced bending moment in the pylons as shown here. and this is the final completed state. So you can see the behavior of the structure right here. So as desired, while we are doing the suspension bridge, the deck should not get any bending moment. We are able to achieve that configuration. You can see the cable forces by switching to truss forces here and click apply, and they are given right here. And you can plot using the step stage graph again all the variations that are occurring in the pylon and the cables. So what I'll do is, and you can plot multiple graphs, so let's try that. I'll change the function type to truss forces, click add new function, and the name will be cable force. The element will be, let's say, this element. Oh, there's an overlapping, let's say yeah, let's say 143. Just making sure that it's a cable element. Force and ith end, click OK, and let's have a beam force function for right tower, or tower axial force, maybe that would be a better name. And the component will be axial at ith end and force, then click OK. Oh, sorry, my bad, I didn't enter the element number. Tower axial force, let's take this element. .61, let me see. So this is the element that we are looking at, and ith end of it, and axial force, click OK. And now I can just select multiple graphs to be plotted on the same stage step x-axis, I mean against this x-axis, and the name can be cable and tower force. Click graph, and this is what you'll get. So you'll get two graphs against the construction stages step. The red one representing the cable force, green one representing tower axial force, and again it is the last stage is right here. So it is the backward direction. So basically this is the initial stage, this is the final state. So you can see how the cable axial force is developing and how the axial force in the column or the pylon is developing. So all these graphs and tables can be easily extracted and generated in your report, and in no time you can come up with the complete model and the design results for such suspension bridges. So that was all I wish to cover today, and I'm just in time. It's 4:30 p.m. in my office in New York. So I as mentioned, it was 1.5 hour session and we are able to meet that timeline. So if you have any questions, you can feel free to ask me now. So you can write to me at asharma@midasyuser.com. Please ignore my phone number for the timing, because or let me give you my other phone number, because this line will this number is soon to change. So my new number, my current number is 646-703-2794. You can reach me at this number. This is my personal number, but anyways, till the time I have something to share with you, you can definitely use this number. Stanley here is asking what's the website to for downloading the tutorial. It is en.midasyuser.com. Let me write that down here. It is en.midususer.com. E is small here. So if you go to this website, it'll look something like this.